Alright, so let's look at this question. It's saying the low melting point and the high solubility of LiCl in organic solvents. Note this. Note this, right? This is saying organic solvents. This is not saying polar solvents. This is saying non-polar solvents majorly, right? Is due to, let's read it out, covalent nature because of polarizing power of small lithium plus ion on Cl minus ion. Yeah, that's kind of true, right? Because Li plus and Cl minus, well, theoretically we thought they would be ionic. Correct, no? And for ionic compound, it would readily dissolve in a polar solvent because the solvation will be very easy. But the small Li plus, right? The small size of Li plus gives it a high charge concentration. It's a very small ion with +1 charge. The charge becomes highly concentrated. Unlike something like cesium plus. Cesium plus is huge. The +1 charge, the same charge on lithium plus, the same charge on cesium plus. On cesium plus, the charge is distributed. Right? Right? On Ni plus, the charge is concentrated. That concentration of charge, what happens when it is brought in the vicinity of Cl minus? Cl minus, already a third period element. What? Cl, chlorine, right? Already a third period element. Right? Already quite large. Then you add a negative charge on top of it, it becomes even larger. Already relatively quite poor Z effective, right? As compared to lithium plus, right? 1s2 configuration. It has gone, the electronic configuration wise, it has gone to the first period, right? So basically, it has become quite large. The outermost electron of Cl minus is quite far away from the nucleus of Cl, right? And so the pull on the outermost electron of chlorine, right? Chlorine's nucleus's pull on the outermost electron is relatively weak. In the surrounding of that Cl minus, you bring Li plus. What's going to happen, right? You have Cl minus, you have Li plus. Distortion of electron cloud is going to happen. Distortion. Right? Because of that, there will be some region where the electrons of lithium and chlorine will be coexisting. That region will be called as an overlap. Hence a covalent character. Hence a decrease in the ionic character. Now, because of its ionic character, it was readily soluble in polar solvents. Decrease in ionic character, increase in covalent character, solubility in polar solvents decreases, solubility in organic solvents increases. Right? Okay, and that is what we have. Now, yeah, this option seems correct, but let's read out the other ones as well. Very low lattice energy, no. Well, still, LiCl does turn out to have, a decently good, or I would say, decently high lattice energy. Unlike that, so yeah, this statement is not true at all. Low hydration energy of Li plus in water. No, Li plus alone is a very small ion with a very high charge concentration. So Li plus, right? Let's say you have LiF, wherein the polarization would be not as much, right? Let's say via this or via some other method, you are able to generate Li plus in water, let's say. It is a very small size with a very high charge concentration. The H2O are going to bombard on it. They are going to, get attracted to it. Right? Like moths to a flame. They are going to attract it to such a high charge concentration. In fact, remember, hydration radius. Lithium plus has the highest hydration radius, hence the lowest ionic mobility within its group. Why? because it has the highest hydration sphere. It has layers and layers and layers of H2O around it. So no, it has actually a high hydration energy, right? Low hydration energy of Cl minus in water. Well, it's not as low, right? To be honest, after F minus, there is Cl minus, right? So if you're comparing apples to apples, if you're comparing F minus, Cl minus, Br minus, I minus, no, it's not that low, to be honest. And then again, it does not explain why LiCl has the low melting point and, high solubility in organic solvents. No, it does not explain that. Right? So the high solubility in organic solvents because of increase in covalent character, right? The low melting point, increase in covalent character, then again decrease in ionic character. All right, cool. And with that, I think option B, C, D are not enough or sufficient, or some of them even correct. They are not, some of them even are not correct to sufficiently, explain the statement. And among these four, option A is the only option which has shown itself to be capable enough to explain the statement above, right? Rightly so, because the question was, this and this is due to. So it was asking for an explanation. Only option A suffices to do that. And with that, we'll say that option A is %% our response to this particular question. All right, let's look at this question. What is it saying? It's saying the compressibility of a gas is less than unity, right? The compressibility factor of a gas is less than unity at STP. Okay. Therefore, its molar volume is, let's see, okay. So compressibility factor is less than 1. But what is compressibility factor? Well, it's molar volume of the real gas divided by molar volume of the ideal gas. Further, this has, put some conditions on top of it. So it has put STP as the condition. Okay. With that, the denominator over here, the molar volume of the ideal gas at STP becomes basically what? 22.4, right? Although, there are some discussions, and IUPAC has released a new standard regarding what STP is, right? They have changed the standards from ATM to bar. But when I'm saying that at STP, the molar volume of an ideal gas is 22.4, I'm taking the pressure, standard pressure, as 1 atm. All right. So far, we don't know whether J is going to follow the new standard or the old one. If it does follow the new one, we'll inform you. If it does keep the old one, we'll inform you as well. For this question, this sole question, however, I'm taking the standard value of pressure in STP as 1 atm and not 1 bar. All right. So if that is the case, what we can clearly see is that, V molar real at STP is obviously going to be less than 22.4 liters. And with that, I think we can clearly see that option B, B for Bombay, B for Bangalore, the sweet B over there, is indeed our correct response for this particular question. All right, let's look at this question. Let's see what this question is saying. It's saying, what is the amount of heat to be supplied to prepare 128 grams of CaCO2 by using CaCO3 and followed by reaction with carbon? Okay, reactions are this and this. So what is happening? It has CaCO3, it produces CO and CO2, then CO reacts with carbon and gives you CaCO2, and basically this is solid, right? This should be solid. And we have CO gas here, right? So what do we see here? We decompose CaCO3, CaO solid gets formed, CO2 gas dissipates, right? If you have an open beaker, you have CaO solid remaining and CO2 gas dissipates, gets away, right, into the atmosphere. Then only CaO solid is there. Then you take that and you take carbon solid, right? And you make them react somehow and you get CaC2 solid and CO gas, carbon monoxide gas. That also spreads around in the atmosphere, leaving CaC2 behind. Okay, all right, cool, yeah, fine. Now, the point is, you know what? These are the reactions and these are the delta H values that have been provided with respect to them. Delta H naught values, to be more correct, right? Okay. What is the amount of heat to be supplied to prepare 128 grams? Okay. Now, one thing is cool, right? So, if, for example, hypothetically, if we had, two this thing here, 2 CaO, right? Then I would have to, take this reaction, multiply this by 2. Take this value, multiply this by 2. Why? Because I want to cancel CaO. I want to say whatever CaO got generated in the top reaction got completely consumed in the second reaction. So I want to get rid of CaO. But the good thing is here, I have the stoichiometric coefficient of CaO as 1 in both of them. So I don't have to do anything. I just have to take both of these reactions, I have to multiply them by 1 and combine them, add them. That also tells me that I have to take these values and add them directly. No multiplication with any number, right? So delta H naught for the whatever you want to call, let's say the final reaction or let's say the third reaction is actually going to be 42.8 plus 111. Right? With that, we know something like this, and we have 3 over here, we have 5 over here, we have something like this, kilocal per mole. Okay. Now, the point is, the question is asking what amount of energy will be required to prepare 128 grams of CaC2. Okay. For this thing, how much CaC2 is getting formed? Right, all of these kilocalories, right, they are per mole, right? Although it is not mentioned, it should have, but they are per mole, right? This also is per mole. So this is for 1 mole, right? So sorry, all of these values are per mole, right? So, and as you look at the reaction, we see that 1 mole, right? 1 mole of CaC2 is getting formed. Right? This much energy should be provided for the formation of 1 mole of CaC2 via this reaction sequence. Right? So 1 mole of CaC2, how many grams is that? That essentially is equivalent to basically what? 40 plus 24 grams, correct? So what is that? 64 grams? However, the question is asking is, I want to prepare 128 grams. You want to do double, right? You want to do double. So you're going to have to require double this energy. Which energy? Double this energy, right? So you're going to require what? You're going to require 307.6. Oh wow, we have this value here. Awesome. So we're going to require 307.6 kilocal of energy to produce 128 grams of CaCO2 via this reaction sequence. And with that, this question is concluded and the correct option, the correct response for this question is option C for Calcutta. Thank you. Alright, let's look at this question. It's saying which of the following oxide is expected to react readily with NaOH. Let's look at this, right? So we have a couple of oxides here. Let's try to find out which acid or base they are the anhydrides of. So what? So look, I'll do this one thing the reverse way, right? So you take 2 NaOH, right? And you subtract H2O from it, right? You take 2 NaOH and you subtract H2O from it. What do you get? Na2O, right? Okay. Similarly, you add H2O to this thing. What do you have? COH twice. You add H2O to this thing. Okay. So I'm going to add this thing over there. No, not this one, right? NO is actually a neutral oxide. All right. And you add H2O to this thing. And what do you get over here? You get essentially what? H2Cl2O8. Well, instead of writing this, I will rather write 2HClO4. Right? Now, if you want to know, right, NO and some other oxides are neutral, remember those ones. Right? Remember those ones, the neutral ones. For the other ones, what you should do is that, in most of the cases, try and find out which acid or base they are the anhydrides of in most of the cases. That should work out. Now, as you can see over here, if Na2O is an anhydride of NaOH, Na2O will be a basic oxide. CaO will be a basic oxide. So it will not react with another base, NaOH. However, Cl2O7 is an anhydride of HClO4. So it's an acidic oxide, so it will react with NaOH. The neutral one won't react, as the name suggests. With that, this question is a go. This question is done with option D, D for Delhi, being the correct response for this particular question. Alright, let's look at this question. Let's see what we have. So, the Kw for water for the following equilibrium. Okay, which equilibrium? Oh, this equilibrium. H3O plus OH minus. Okay, this is what we have. Changes from this thing at this temperature to this thing at this temperature, right? H3O plus. You read it there? Read it carefully. What is written? H3O plus in the subscript. Plus OH minus in the subscript, right? Okay, cool. It was getting congested, so I asked. Calculate the pH and nature at 60 degrees Celsius. Okay, cool, fine. So, think about it, right? What do we have here, right? At 60 degrees Celsius. So, at 60 degrees Celsius, Kw is what? 9.62 into 10 to the power minus 14. But it's always going to hold true that Kw is equals to H plus concentration multiplied by OH minus concentration. Well, yeah, the question has written H3O plus. I just write H plus instead. Either way is fine. To be honest, you can write it either way. Okay. Now, what do? We know that, this is pretty certain that since you have not added any acid or base, the solution is obviously neutral. Okay. That tells you that H plus ion concentration is equals to the OH minus ion concentration. You can replace, let me use a different color. You can replace this, right, with this. Yes. So what you can say is that, you know what? Kw is actually equals to H plus multiplied by H plus concentration. That is H plus concentration squared. So, H plus concentration is equals to under root Kw. Okay. pH is equals to minus logarithm of under root Kw. Okay. It is equals to, now I'll take the half away, right? In the power, I'll take the half outside of the log, right? So I will have minus half logarithm of Kw. Okay. Now what I'm going to do is I'm going to, continue my calculations over here. With that, I'm going to bring into the field a new marker. Okay. So, pH is equals to minus half logarithm of Kw. What is the Kw value? This much, right? 9.62 into 10 to the power minus 14. Okay. So pH is equals to minus half logarithm to the base 10 of 9.62 multiplied by 10 to the power minus 14. Okay. Let's solve it out. So I have 1 by 2. The minus has now gone inside. Sir, what did you say? The minus has gone inside. So I have plus 14 and I have minus logarithm of 9.62. Okay. So I have 7 minus 1 by 2 logarithm of 9.62. Now, I'm going to make an approximation and I want the permission of you guys to do that. Can we please can we approximate 9.62 as 9? But sir, why do you want to do that? Well, I want to do that. Why? Because it will be super easy for me. Sir, how? Because now I can write it as logarithm of 3 square, right? And I know the value of 3, right? Log 3, sorry. So this is going to be, 2 is going to come outside. Logarithm of 3. Logarithm of 3 is approximately 0.48. So here we have 0.48. So pH is coming out to be 6.52 approximately. Okay. Now the point is, let's look at the solutions, right? pH is this much. So this is out of the window. This is out of the window. Solution is neutral. Look. This at 25 degrees Celsius, Kw is 10 to the power minus 14. So pH scale ranges from 0 to 14, right? If at some temperature, the, what do you call it? Kw value turns out to be 10 to the power minus 13. The pH scale would be from 0 to 13, right? And 6.5 would be the exact neutral position. Right now, pH equals to 6.51 as they have written over here, and we found out, right, we calculated 6.52. That's the middle point. That's the point of neutral solution. That's the point of, what did we start with? H plus concentration equal to OH minus concentration, right? This is what we started with. So definitely the solution is neutral. With that, option B for Bombay, Sweet Bombay is indeed the correct response for this particular question. And with that, we can conclude this question.